Greetings, back in my basement yet again. This starts our third week of online courses. It starts a new topic, which is exactly the topic that program 7 is going to be. This is a queue. Now the queue is built out of the same node that stacks and linked lists are built out of. I'm going to write some code. Actually, what I'm going to do is I'm going to take our stack code, our example for the stack, with the app data class. So the class stack and the class app data that gets used by stack. And that app data that was the sensor network nodes. And then I'm going to use that to start the queue code. And so I'm going to cannibalize the code, which means I'm going to make some edits to the code, just to basically show you how similar the code is between these different data structures. So, writing it from scratch, you don't have to write it from scratch, but when you edit, you have to make sure, you have to be careful that you get all the little pieces correct. So I'm going to drop the video. I do want you to be cognizant of your mental health. This pandemic, this crisis is going to eat at you emotionally. It's going to eat at you mentally. When you start to feel bad, when you start to feel overwhelmed, you need to reach out. You need to either call the University Counseling Center, or you need to talk to, if you have a therapist that's not at the University Counseling Center, talk to your therapist. This is, I was talking to my advisor today, my thesis advisor back at the University of Minnesota, and he said the next crisis that we're going to see, the next upswing we're going to see in this crisis is mental health, not the coronavirus, but mental health. And I agree with him. So watch out for your physical health, watch out for your mental health. Okay. Now, with that said, I'm going to drop video, and then I'm going to share out PowerPoint slides. And hopefully, no, that is not what I wanted. That is actually a PowerPoint presentation for some data on our data analysis on a proposal in front of curriculum committee. Or not curriculum committee, Gen Ed committee. Okay. So this is where we ended last time. We did the stream insertion operator overload for stacks, okay? And we got our code up and running. So those operator overloads are going to become important. It's going to just become assumed that you're going to do those, okay? So now, what I want to share out is this. So, slideshow from beginning. Okay, so here we are. Queues. So if you have a list that always adds to the end and always deletes from the front, then this is a queue. Conceptually, the same as a line in a bank. The first person in line is the first person who gets out of line to see the teller. So this is first in, first out, or FIFO. Sometimes people call it LILO, last in, last out. When you come into the bank, you don't enter in the middle, you don't enter at the front, or you don't cut lines, you start at the back, okay? So queues are used a lot in communication systems and in discrete event simulation. In fact, right now, as you're streaming this video lecture, this is using a queue. In fact, we call it a buffer. And so when you see a video buffering, it's filling up to a certain size, a queue. And that way, when it starts to play out of that queue, the packets, the internet packets out of that queue, everything stays in order. And that gives you a buffer so that, you know, if there's some congestion, you can start eating at those nodes in the queue. And when you don't have congestion, you can build it back up so that it's full buffer. So that's just one particular way that a queue gets used. But queues get used in a lot of different ways. And so we're just going to use one sort of in today's lecture in a bit of a silly way. I've got a queue of sensor network nodes. Maybe the sensor network nodes want to contact the mothership and download their data, and it's first come, first served. So that's another way to think about a queue: first come, first served. Okay. Now, more care needs to be taken if you're going to implement queues using arrays rather than dynamic allocation, because that leads to buffer overrun problems. I'm actually uploading 2 sets of PowerPoints, but I'm only going to do the dynamic queue PowerPoints. The array-based queue PowerPoints are there for you to look through, but I'm not going to lecture on them, and I'm not going to test you on those. The reason I'm putting them there is actually for the computer networking people. So if you're a computer networking person, you will deal with queues that are implemented in arrays, queues that are buffers that are susceptible to buffer overruns. And so the buffer overrun problem is something that IT and system administrators and system designers need to know about. And so that's our computer networking people. Computer science people need to know about it, but not at such a deep level unless they're going to work in operating systems. Okay, so here's a common queue. People enter at the back and people leave at the front, and the flow of people follows along the large arrow. So that is, you enter at the back, you walk, you slowly shuffle up to the front, and then people leave and get serviced. Okay. So how to build queues. Dynamic allocation offers some advantages. We only use the amount of memory needed, and there's no hard limit on the size of the queue. The queue can grow as large as we want it to, as large as our available memory is. However, it requires pointer manipulation, and the pointer manipulation can cause memory leaks. Arrays can be used, but there's a lot of boundary conditions in the arrays. When you mishandle those boundary conditions, that's when you open yourself up to buffer overrun problems. So for those, I strongly suggest that all of you look through those slides that I'm posting for the array-based implementation of queues. But at the end of the day, that's much more important to understand when you're going to be working inside of hardware. So computer networking, computer engineers, you need to understand those array-based queues or buffers, okay? Computer science needs to understand them as well, but not to the same depth of understanding. So queues versus stacks. Stacks, queues, and linked lists all use the same node structure. You've got application data, and you've got a next pointer. It's implemented in a struct, same way it was in the stack programs, as it will be in the queue programs, as it will be in the linked list programs. So stacks and linked lists use a pointer also to the first item. And that's usually called head or front or top. If it's called top, we usually just use that for stacks, okay? Now a queue uses the same front pointer, but it also needs a back pointer. And that back pointer is used to keep the address of the last node in the queue. Because remember, people enter at the back of the queue, and depart from the front of the queue. So nodes need to be allocated at the back of the queue as something new comes in, and the nodes need to be deleted from the front of the queue. So that back pointer leads to efficient implementation. Otherwise, every time we would insert, we'd have to walk the entire length of the queue to find the back. Now, you've been in these jumbled situations, right? There's a line, and it's not clear where the line ends. Maybe it's at the concession stand at a hockey game. Maybe it's at the self-checkout at the grocery store. And you're going, are you the end of the line? No. And you keep walking through going, are you the end of the line? No. Are you the end of the line? No, it's behind me. You finally get to somebody and you're like, are you the last person in line? Yep, the end of the line's right behind me. That's the kind of thing that you would have to do without the back pointer. Don't want to do that. That takes a lot of time. It's really frustrating, right? So here's some pseudocode for insertion into queues. We call the insertion routine for queues NQ, okay? And so we're going to need a front pointer and the back pointer and the data we're going to input. If QBack is equal to null, then we need to allocate a new node, and we're going to copy that new node's address into both QBack and QFront, okay? So remember, these pointers are pointing at physical memory. In this case, with the empty queue, so when QBack is equal to null, we know that's an empty queue. They're both going to be pointing to the same node because that person or that thing is both the front and the back of the queue. We copy the data in, we set the next pointer to null, and we're done. If QBack is not null, then, and it doesn't matter if QBack is null or QFront is null. We can check either one because in an empty queue, they're both null. So otherwise, you know, this is the normal case. QBack arrow next is where we allocate the new node. So QBack arrow next is going to be null. We're going to allocate a new node into it. We're going to move the QBack pointer so that it points to that new node. And then we're going to copy in the data and set the next to null. Okay. Now, if we look at the special cases, remember I've said before about special cases, a stack only had one special case, and that was the error case for deletion. A queue has a special case for insertion. And we have that one special case for the empty queue only because we have two pointers to worry about, not just one. So we have both the front and the back. And so to make sure that that gets handled correctly, on an empty queue insertion, we need to fix both of those pointers up. In the stack, we just allocated into, we copied out the address in head and then allocated, hooked it up, and we were done. And so that wasn't a special case because even when the head was null, everything worked out. For queues, got to have that special case. Deletion for queues, again, we just need QFront and QBack. If the QFront is null, then that's an error. If the QFront is not equal to the QBack, so they're not pointing at the same node, which means there's more than one node in the queue, then we copy out the data out of QFront. We save QFront's address into temp. Then we move QFront one deeper into the queue. So that's going to be the new front of the queue, right? When a person leaves the queue, the person behind them, the next person in line, becomes the front. And then we free temp. And that's actually called delete. And I'm not sure why I used free here. Free will work as well. That's a C deallocator. So actually, let me go in and change that right now. So there's the delete. And then I'm going to change the free down here to delete as well. And there's the delete. And so there we go. So back from this current slide. Now we're using the proper name for C++ deallocation, which is called delete. Okay, so we just took care of the special case, or the normal case, excuse me, for when there's more than one thing in the queue. If there's only one thing in the queue, that's the else of this if statement. And so that means that we copy out the data and we just directly delete queue front. We don't need to use a temporary pointer. And we set queue back equal to queue front equal to null. So queue back and queue front are both set equal to null. And then the last thing we do at the bottom of the dequeue routine is to return the data. And so that's the deletion part, okay? So if you look at that code, dequeue has two special cases, okay? It has an error case for when we try to dequeue from an empty queue. That's just like pop and stacks. You know, we had to have that special case for pop if we were trying to pop an empty stack. But then we also have a special case for when deleting the only node in the queue. And this is caused by having both a front and a back pointer, just like the special case for the insertion. When both of those pointers are null, you have to special case that. When both of those pointers point to the same queue and we're deleting, you have to special case that, okay? So that's two special cases. So compared to a stack, which had 0 special cases for push and 1 special case for pop, a queue has 1 special case for enqueue and 2 special cases for dequeue. So the number of special cases has gone up, which means the number of if statements went up, okay? Now there's lots of applications for queues. The most common use is in communications and communication streams. I/O often has a queue associated with those streams. And in fact, when you use cout and cin, those have queues. Those are implemented using a buffer or a queue behind the scenes. You don't see it, but that's what's going on. Same thing when you use file input and file output. In fact, in file input and file output, your program has a queue, and the operating system, which is handling all the file input and output, it has a queue as well, or a buffer. So one of the ways to think about this is imagine an asynchronous source, like a communication link, and a synchronous destination. So video streaming, YouTube, etc. Because of the way the internet works, that's asynchronous. And the stream you want to watch synchronously. You want to see it as if it were synchronous, okay? And so you don't want it to stop and stutter. You want it to run smoothly. And that's what the queue gets you, okay? Voice over IP, same thing. So all of our phones on campus now are VoIP phones, VoIP, voice over IP. They're gonna have queues in them to buffer, and on the voice over IP, you don't want to buffer too much because then you start to get lag. So I'm sure you've all seen lag when you're doing Zoom or Big Blue Button stuff for your classes, right? Some people lag. Sometimes you can even hear yourself echo as your voice comes out in the classroom or on the instructor's computer and then gets fed back in through the microphone. So that's where that echo is coming from, because there's a buffer in there, okay? So here, graphically, I'm just gonna go through the enqueue routine. So enqueue, the empty queue case, you got front, you got back, and they're both null, okay? So we're gonna get some new space, and in this case, I'm gonna separate how we deal with front and back. In the code, I sort of strung it together, the pseudocode. So we're gonna allocate new space into front. So that new space is a physical allocation, we say new, and that is a struct that has the app data in it and a next pointer in it. And right now that's garbage. The app data is garbage and the next pointer is garbage, okay? We don't have anything that causes that to be zeroed out, okay? Then we're going to copy front into back. So back equals front. And that means that both back and front are pointing at exactly the same address, exactly the same node. We then set our next to null. So that's, whoa, bad slides. Well, that is weird. From current slide. Oh, there's an animation in there that I didn't delete. Okay. New space, copy front into back there. And then just ignore the animation. So now we're copying next into, we're setting next to null here. That's annoying me. I'm gonna drop out of here and see if I can get into that animation and get rid of it. Remove the animation. There we go. Okay, so let's see if I manage to get this. New space at the front, copy front into back, and no, I removed the animation on the wrong slide. So undo that, go to here, show the animation pane, remove it, from the current slide. Holy moly. Okay, so copy front into back, which we do. And then on the next page, that's exactly what I wanted. So on the next page, we set next equal to null. Okay. Then we copy the data in. Oh, bad animations. And then we're done. So general insertion, and I bet you I'm going to have some animations screwed up in here because I was copying slides and adding to them. So general insertion, we're going to insert at the back, okay? So I'm just taking this to be a single character as our data. So we're going to new space at back arrow next. So we're going to allocate memory into back arrow next. So that does that. Remember that new space and the next pointer both have garbage in them. We have to copy over that garbage to make it all work right. So we've copied or we've created this new space. Then we need to move back to back arrow next, which is right there. Then we need to set back arrow next to null. And that's what we just did. So from here, remember that next. So that next right here has garbage. This new space has garbage. And so we need to make sure that that becomes null. Okay. Then we copy the data in. Bad animation. Boom. And there we go. Now this is actually the queue that works the internet. This is a queue, you know, there are billions of these queues running right now in the world, and they're just passing characters along. The internet, TCP/IP, is based off of characters. Everything is translated or coded as a character. So bytes by byte by byte. A character is 1 byte in size. So let's go on to deletion. Notice that I've got some extra stuff here. I've got a temp pointer, and I've got a app data variable that has some uninitialized data in it. Doesn't matter, okay? And so for my normal deletion, The first thing I'm going to do is copy front into temp. So I'm going to make temp point at the same node that front points to, like that. Okay. Now I'm going to move front to front arrow next. Remember, the first person in the queue, the person at the front of the line, is going to be moved along to, be serviced, whether it's a checkout or a bank teller. And so the new front of the line is the second thing in line. So we move that front pointer to the second thing in line. We still haven't processed the first thing in line, okay? So when that first person gets out of the line, they still have to be processed. So I'm going to process that by copying data out of temp arrow data. So I'm going to copy that data, that single character, out of there, and I'm going to put it into that uninitialized data. So that's a variable, that's an app data variable, and now it holds the single character that was at the front of the line. Now I can delete temp. So this is returning that address, that memory, to free space. Temp is still pointing, when you get done with a delete, temp is still pointing at that old memory, but that old memory isn't useful anymore. And so temp's essentially pointing at garbage, okay? We haven't nulled it out, it's just pointing at garbage. And then we return the data. So we're gonna return that to whomever called DQ, okay? And so now our queue has reduced in size by 1. We've freed up the memory. If we don't delete that memory, that causes a memory leak. That's a bad thing. So we've gotten rid of that memory. It's been returned to free memory. And when our DQ member function stops running, temp will be deallocated and therefore no longer point at free space. Okay. Now here's our special case when we try to when we're dequeuing the last element, the only thing in the queue. So at the end of this, both front and back have to be null. Okay. So we recognize that front is equal to back, and we're going to copy the data out. So take that data, put it in there. Okay. Now we just delete front. So both front and back are pointing at garbage. And that's not the way an empty queue should look. An empty queue should have both front and back being null. So we're going to copy both front and back, or we're going to set both front and back equal to null, like that. And then we return that single character, okay? So whoever called DQ, they get back that data, that app data. And I just used a single character in this because this is the vast majority of the queues running in the world. Every router, every switch, every hub, every computer, every network interface card is running multiple queues that store single characters. That's what they do. That's the way the internet works. Okay? So that's all my slides for dynamic allocation of queues. So I'm going to drop the share here. And then I'm going to share a new screen. And lecture 9. Yep, here we go. So all I've done in here, let me clear all this this junk off of here. Clear. Okay. So all I have in here, there's my 2 PowerPoint sets of PowerPoints for today's lecture. I've copied over appdata.cpp, appdata.h. stack.cpp, stack.h, and ex8.cpp. Okay? So I'm going to start by building our queue out of this stack stuff. So the first thing I'm going to do is I'm going to rename stack.h to queue.h. Then I'm going to go in here and edit queue.h, and I'm going to build my queue reusing the code in stack. So right here, I'm going to change the ifdef to queue. I'm going to change the class name to queue. I'm going to change the constructor to queue. I'm going to change the destructor to queue. And this is not the correct .h for stack. I am going to stop the lecture right here, and I will fix all this. Whoops. I will fix all this, and I will have a chunk 2 of the lecture, because for whatever reason, well, actually I can pause the recording. I'll pause the recording, and then I'll be back with part 2 when I figure out what happened to my stack.h and my stack.cpp that I. Okay, I'm back. I was just being stupid. This is what happens when you aren't getting enough sleep. We had put those operator overloads into app data, not into stack. And so actually I was editing the right thing. So I'm going to share back out that file. You can see me bouncing up and down through here to make sure what was going on. So I'm going to go back into that stack.h that I renamed as queue.h and continue altering this. Okay. So I'm starting over again. So here we're going to change this to queue. And these are the preprocessor commands to prevent double including or double defining things. I'm going to change our class name to queue. I have to change our constructor to queue. I have to change our destructor to queue. I'm going to change push to enqueue. I'm going to change pop to dequeue. Is empty, I'm going to leave the same, and print stack will become print queue. Okay. The struct is going to get renamed as QNode. And then the pointer in the struct also has to be of type QNode. Okay. Down here, we've got stack node. That needs to be a QNode. And then I'm not going to call it head. I'm going to call it front. And I need another one called back. That's it. See how easy that was to alter my stack node or my stack specification into a queue specification. So I just changed every place that said stack and I made it say queue. And then I added this one pointer right there because I need a back pointer. Okay, that's it. So now I'm going to move the stack.cpp to be queue.cpp. And I'm going to edit that and again alter it into what I need. So here we go. Remember, everything that's stack becomes queue. So I'm going to include the specification for the queue, the constructor becomes Q, and the scoping operator. So the scope has to be Q as well. Here, head is now front. And I'm going to need another thing in the constructor that is back equals null. Okay, we want to make sure that both of those pointers are null now. The destructor has to be the destructor for Q. That has to be Q for the scoping operation. And while not is empty, DQ. That's it. Is empty is, is exactly the same as it was before. And so all we have to do is while the queue isn't empty, we DQ things. And that's our destructor. Down here, the scoping operation needs to have that Q, and then push has become NQ. Okay? So, this changes quite a bit more. Okay? Whoops. I jumped all the way to the bottom. So NQ, I'm just going to get out of here and delete this whole thing. Okay, I could have reused some of that, but it's really not what I want to do. Okay, here I've got that first special case. If front is equal to null, okay, so front equals a new Q node. Okay. And then back is equal to front. So now front and back point at the same node. I copied the data in. So front arrow data is equal to the data, which is the parameter to the function. And then front arrow next is equal to null. Remember, there was an else on this. This is the normal case else. Okay. So in the normal case else, go back and look at those PowerPoint slides. But we were supposed to, actually, I do have the PowerPoint slides right here. I'm going back to my pseudocode. Okay. Sorry about the blocking off the screen there, but I wanted to get to the pseudocode for insertion for the Q. So the pseudocode for NQ. And it says that the back arrow next, so I called it Q back in the slides, but in our code, I'm just calling it back. So back arrow next is a new Q node. Okay. Then I'm going to move back. So back is equal to back arrow next. So that moves back so that it's pointing at this new memory I just allocated. That new memory has garbage in it, so we got to fix up the garbage. So that's back arrow data is equal to the data, which is what we passed into the NQ routine. And then back arrow next is equal to null. Now, I want you to notice something here. And this is just some code weirdity stuff. I really hate the highlighting here. These two lines of code, okay, could have been written with back, because really front and back are pointing the same place right now. So I could have said back arrow data, back arrow next. So let me go up and change that. And there's a reason for me to change this, and I'll show it to you in just a second. So this makes no change to what's actually going on, because front and back in this special case are pointing at the same memory location. So now that I've changed those, okay, so looking at those two lines, now we can see that those two lines are exactly the same as those. If we wanted to, we could take those two lines out of the if and the else and put them after the if else, and only write that code once. So if I wanted to do that, I would do, so I'm just deleting those two lines. I'm going to drop them in right here, re-indent them. And then I can delete them out of the if as well. This is exactly the same, okay? Doesn't matter how you do this. The sequence of the instructions is the same. You allocate into front, you set front equal to back, you set back arrow data to the data, you set back arrow next to null. If it's not the special case, back arrow next equals new, back equals back arrow next, back arrow data equals the data, back arrow next equals null. So those two, we reduced the size of this and we put those right there. So I'm going to leave it this way, because I think at this point, it's easier for you to understand if all of that code is in one block. But just be aware that sometimes we don't need to duplicate that code in each of the cases if the code is always the same. So, and in fact, I'm going to change this back to front as well. That way, yeah, I guess I do. I do want to leave that as front. Okay, so that's our enqueue. Now I've got to write dequeue. Dequeue, again, right here, is scoped inside of the class queue, and it's no longer going to be called pop, it's going to be called dequeue. Okay. We need that local variable, the data, because that's what we're going to return. And then stack node is not a stack node anymore, that's a queue node. And temp does not equal head, we call it front now. If is empty, return the data. That's our error case, okay? But we need another special case, okay? So again, I'm gonna go over, I'm gonna look at the pseudocode for that, okay? And the way I wrote the pseudocode, I basically asked the question, if front does not equal back, okay? Now I'm going to turn off that stupid automatic indentation for Vim. Okay, So front is not equal to back. We need to copy the data out. So the data equals front arrow data. Okay. We need to set the temp pointer equal to front. Let me give you a little bit of space here. And then we need to move front. So the front of the line is getting deleted. So the second thing in line becomes the front. So front is now equal to the second thing in line. That's front arrow next. Okay. And then we need to delete temp, return it to free space. That's our normal deletion. If front is equal to back, that's the else, then we need to make sure that everything works correctly. But this is actually less code because we don't need temp here. So the data equals front arrow data. And then we just immediately delete front. And we set front equal to null. And we set back equal to null. That. I scroll down a little bit. No longer need that, no longer need that, no longer need that. And we just return the data. So there's our dequeue function. Is empty for the queue, needs to be scoped for the queue, and return it's not head equaling null, but front now equaling null. If front is equal to null, then it's empty. So that returns true. If front does not equal null, this will return false. Print queue becomes print scoped inside of the queue class, print queue. Okay. We need a queue node. Temp equal to front. Change this to be queue contents. While temp does not equal null, cout temp arrow data, cout end line, temp equals temp arrow next, cout done, return. All of that code is the same. It's absolutely the same. All we did was change the scoping operations from stack to queue, the name of the variable head to front. We added back, we added the code for handling back, okay? And added the special case code, and we're done. We changed push to NQ and pop to DQ. So a lot of that code was reusable. A lot of that code we could go through and reuse, okay? We had to alter it, we had to edit it, but writing code from whole cloth almost never happens. We almost always take code that we've developed prior, copy it, alter it, make it work for the current situation. That's what we did right here. Okay, I'm going to jump out of this. And the last thing I'm going to do in this lecture is I am going to, actually I'm going to rename this ex8.cpp to ex9.cpp. And then I'm going to vi ex9.cpp. In here, again, I need to change my include. Just like I did in q.cpp, I need to include q.h. App data is the same. The stack is now a queue. my Q. This becomes Q. This becomes NQ. This becomes print Q. In the object my Q. And then while my Q dot it, while not my Q is empty, this is my Q dot DQ. That's it. That's absolutely it. Okay. And I just created a test program. This will enter 3 things into the queue, and we'll print out the queue and then print them out one by one. These, I'm gonna, boy, if I could remember what did I use last time? Sensor ID 42 was first, 2525 was second, and 2112 was third. So I'm gonna do the same thing. When we did that last time with the stack, we saw them come out in reverse order, 2525, then 2112, then 42. But now we'll see them come out in order. Remember, first in, first out. So I'm gonna compile this. EX9 is gonna be my executable, ex9.cpp, app data.cpp, and q.cpp. I gotta think I'm gonna get some compile errors here. I mean, I altered a fair amount of code, and sometimes it just frickin' works. Oh my goodness. So EX9, okay. My virus scanner has to make sure that this isn't some sort of virus that I've created. If only we had a virus scanner for coronavirus. Maybe we will. Maybe we'll get this down to you know, a really short test. So the first one, my sensor ID is 42. The latitude, remember that one was below the equator, so I'm going to do the same thing again. Longitude, somewhere in the Western Hemisphere. Value of the next reading. So this is all of the readings for this sensor. So I'm going to put those in as 1, 2, 3, 4, 5. Next sensor ID is 2525. Its latitude is in the northern hemisphere. And so that's going to be what am I going to make this as? I'm going to put it at about 38 degrees north. And longitude, negative, what are we doing? What are we doing here? Negative 92.12 degrees west. That's going to put it in about Oklahoma, I think, if I remember my latitude and longitude right. Their readings are going to be the next, so 6, 7, 8, 9, 10. And then sensor ID 2112, which of course is a Rush song, so that should be approximately Toronto. So that latitude is about 42 degrees, whoops, not negative, 42 degrees north. And a longitude that is just short of ours, which is probably, let's see, it's probably around 81 degrees west. And their readings are 11, 12, 13, 14, 15. we should see them printed out in the order, you know, in the queue, the same as if they were in the stack. 42 is the first, then 2525, and then 2112. But then when I run that while loop, I'm going to be dequeuing instead of popping. So the stack put them in reverse order. So it would be 2112, 2525, and then 42. The queue keeps them in order. So up here, here's the queue contents. 42 is at the front of the queue, then 2525, and then 2112, and we're done. And they come out in order. First in, first out. Second in, second out. Third in, third out. And that's today's lecture. With all of that said, you know, I want you to stay engaged with your classes. I want you to stay safe. Don't gather. Don't visit friends. I am fairly certain that we have coronavirus cases among students and coronavirus cases among faculty. I have heard from 3 students, or actually Zoomed with 3 students, that I am fairly certain have coronavirus. And I know of 1 faculty member that is fairly certain that they've had coronavirus and they're on the road to recovery. This is not meant to scare you. I hope it doesn't crank up your anxiety, although it probably will. But when you get, you know, a temperature, if you start coughing, contact your primary care physician. If you can't, then contact War Memorial Hospital and, you know, ask them, do you need to see me? Do I need to get tested? We don't have a lot of test kits up here, but stay away from people, stay home, stay safe, and the life you save might not be just your own. The life you save might be other people's as well. You know, the people who stay home are heroes. And with that, we are done.